So that's illustrated here. We've taken a very simple problem, just so we can draw it on our slide, of a scientific simulation with 16 points on an edge. Typically in a scientific simulation, they have boundary conditions, so you know the value of the quantity on the edge. And you have, in the middle of that region, you have 14 by 14 points. And those are what you want to determine. And then the value at a point like this is determined by its 4 neighbors. That's a classic nearest neighbor structure used in Laplace's equation for this problem. Now, if we were doing this on a single core, we would actually take this big 16 by 16 mesh and stick those points in a single core and write the algorithm for that core. If we want to run it on 16 processors, or so, which is today 16 cores, we would chop this problem up into 16 parts. So each core only has 16 points, 4 by 4 little domain here, and it's solving the same problem in this subdomain. And so this illustrates an incredibly key feature of all of these parallel processing problems. You take your original problem, you think of its algorithm, you chop the problem up into parts, and then you find the algorithm appropriate for this part. Lots and lots of problems have the feature that the algorithm for a part is closely related to the algorithm for the full set. And so that you can actually take essentially the same code that you wrote sequentially and modify it just a little to use it in parallel. This is the origin of something called single program multiple data, that the multiple data are these 16 data groups here, and the single program says we run the same algorithm on each of these 16 cores, and they're actually doing different things because the data in each core is different. In fact, there's different amounts of data in each core. This core here has 16 independent points. This core upper in the corner, because these boundary conditions are known, only has to find 9. But they're more or less solving the same problem. They're solving the Laplace's equation in this case in the subregion. And if you read some of my earlier articles, it would explain how the key difference is just in the boundary conditions. If we go back to this one here, this Laplace's equation is defined by the equations of Laplace for each point plus the boundary conditions at the edge. If we go here, this processor up here, well, it's actually got the same boundary conditions as before here, but we have at this edge here, it needs to know the values of these at these points here. So the boundary conditions get actually replaced by a communication step, which communicates information between processes. So this is, again, a key feature of all parallel algorithms. You have a sort of piece of arithmetic running on your CPU. And then every now and then you have to do some communication to get information from the other processes involved in the problem, which tell them information that they know, which you can then use. So this is a general structure of parallel computing, a bunch of cores working together. They do some computing, and then they do some communication. Then they do some more computing, then more communication, and so on. For scientific problems, this is pretty structured. For other types of problems, it's not as structured as I said there, but they're still consisting of cores / processors doing computing and then exchanging information, either by writing it to disk and reading it as in Hadoop, or by sending information over the network, as is in the case of traditional message passing interface, which is used in scientific simulations. Here's a more complex example. Here we have an airfoil, the wing of your favorite aircraft, and you need to try to solve this problem numerically. In the previous case, I had a very simple case where we have regular mesh points, um, and here we have the same type of issue with irregular mesh points. And we have to have irregular mesh points because if you know anything about computational fluid dynamics, all the functions are changing much more rapidly near the wing than they are out in the far away from the wing. And therefore, to make an efficient algorithm, you chop the world up into in this case, so-called elements, because there's a so-called finite element method. And you'll find the elements are bigger out here where not much is going on because things change slowly and they're very close together near the wing. We will find that in order to get a sensible parallel algorithm, we'll do the same thing. We'll take these elements, we'll chop them up into groups, but we will do this in a slightly subtle fashion. In the example here, the groups are all roughly the same size. The groups here will be rather different in geometric size because we'll actually want to have equal number of elements in every processor. And that means that the processors will cover a big area out here and a tiny area here. And that's so-called a load balancing problem, which is sort of non-trivial. And lots of work has been done on how to do that in an optimal fashion. Here's another example of showing how you might calculate the evolution of the universe. This is some early universe simulation done in cosmology. Here's the density of stars. And again, you take your stars and chop the stars up into groups, but put the stars in different processes. But now it's a little non-trivial because by Newton's laws, the stars interact with each other. And we will need to do a rather subtle decomposition to get an equal amount of work done in every node, because whereas in the previous problem, each element only interacted with a few other elements, in the cosmology problem, each star interacts with lots of other stars, but the interactions are only important for nearby stars. And so calculating the total amount of work done by our processors is pretty non-trivial. And so it turns out you again have a so-called load balancing problem, trying to see how to chop these stars up into parts and put the parts in each processor. But it's not so trivial to make the work done, to get a good parallel algorithm, which is sort of naturally defined by getting the job done in the shortest possible time, which corresponds to making certain that each processor / core has the same amount of work to be done. So these are non-trivial. You could call these engineering problems because they really are not hugely difficult, but they do cause a lot of pain and a lot of very important research is done to get this to work well. Here's some other example from a long time ago. We have at the top a little, we have a California, and we imagined that this California had 4 missile sites, and the missiles were launched from those sites, and you were in charge of tracking those missiles and shooting them down. Well, in your tracking algorithm, to get good performance and track them efficiently, you would use parallel computing. And you would probably, again, chop the problem up into parts, make certain one core was doing these 4 missiles here, another one these 4, and so on. So here we have a very different problem, missiles, and but we have still the same idea. We divide the problem up into parts and put each part in a single processor. Another example, which has been implemented many times, especially a few years ago when computer chess was very popular. It's now no longer so popular because computers are just simply too good. and they will beat any human chess player easily. But we have, in the case of computer chess, the way computers calculate, play chess is they do a very brute force method. They start at a particular position. They look at all possible moves in that position, give them one move by, say, white, pawn to king 4, the so-called e4 move. Then they look at all possible moves of black, which is either, in case it might be pawn to king 4, pawn to king 3, pawn to queen 4, and so on. And they build, then they go back to white and they build trees. And what you have to do is build those trees. You look at the end of the bottom of the tree and you score it by adding up the number of pieces left on the board and produce a score for that position. And then you try to choose the move which gives you the best score, assuming the opposition plays the best move at each stage. And this can be done in parallel. Here is an obvious way of doing it in parallel. We take these moves here. We assign each of these moves to a different processor. We calculate the best in each processor, then take the best of the best. And this is all done in a rather subtle fashion called alpha-beta pruning, and you have to refer to the literature to know how to do it completely optimally. But it's still the same idea. You decompose the problem. And here we have moves as the thing we're decomposing. So here is another example, a little related to that cosmology example, where we have a bunch of particles. I've just drawn them in 2 dimensions, and we're trying to chop them up into processors. And here's an example of how to do it. And this is one way of doing it. You chop the world up and you put processor number 1 with those particles, processor number 2 with that, and so on. An alternative is the so-called scattered decomposition. You have still 4 processors. You make a mesh, and so where 1 appears many times, whenever there's a 1, you store that particle in processor 1. And this one here I did optimally, so everybody has 21 particles. For this case here, it's not optimal, we actually have node 1 having more particles. So why would you ever use this? The advantage of this approach is when things move, because these particles will be moving around, and so it's not so obvious when you do this simple geometric decomposition that when they move, you'll keep the load balanced, and in fact you won't. And the advantage of the scattered decomposition as things move around, it will always still be roughly right. It was never perfect at any one stage, but that's a method which is more stable. And this is the optimal method at a particular time. This is a stable decomposition which is probably better to use.